The cyclotron is another way that radioisotopes can be produced. Normally radioisotopes for medicine are produced in a nuclear reactor, or up till fairly recently, a nuclear reactor by neutron bombardment. So molybdenum 98, 42 plus a neutron will give us our 99 molybdenum, which is our source for technetium. Our 99 molybdenum decays to give us 99 metastable technetium 43 plus a beta particle, and that's the one we use for in technetium 99M, in scanning, and that is when it decays, the 99M metastable decays to form this technetium plus L, and this is what we're scanning for with a gamma camera. So this one here produces little radiation, or as low as background radiation. That's what happens in a nuclear reactor. We have this neutron bombardment. However, in a cyclotron, we have a different type of device. It's not a nuclear reactor. It's a device used to bombard target elements with ions. Okay, so they're going to hit our target element. And these ions could be hydrogen ion. So hydrogen with one proton, one electron, with the electron stripped, or an extra electron to give a H- ion. So we need charged ions, either the hydrogen ion or a proton or something like that with a plus charge needs to be used in a cyclotron. Those ions, because they are charged, can then be affected by electric fields and magnetic fields. And that's the principle of the cyclotron, is using those fields to accelerate charged particles to hit a target element. Cyclotron, as the name implies, cyclo, a circle, or is designed to accelerate a particle at an increasing rate and then hit a target, and that target is then affected. If you're shooting protons into the target, you might increase the number of protons in the nucleus. Those protons can then decay later to become neutrons. So unlike a nuclear reactor, which is bombarding with neutrons, a cyclotron uses positive ions, such as protons, to bombard a target element. How does it actually happen? We have two D-shaped electrodes with a gap. We have a source of alternating current, and that can alternate very rapidly, so much more rapid alternating or oscillation of current. A target might be a proton. When this side is negative, this side is positive, the proton is accelerated. Because it's alternating, we have the proton heading this way. This shell, or this D-shaped, is sort of like think of it like a pocket, so the particles can go in and out of these D-shaped electrodes. It might not be called electrodes, but similar sort of thing. As that particle heads this way, and a magnetic field is created. If we want it to turn this way, we'd need a field heading into the page, giving us a force at right angles to the motion of the positive particle. If you remember the right-hand palm rule, our velocity, our field, and our particle will accelerate or turn 90 degrees, the force acting is at 90 degrees to that field, unless there's some other effect. But this particle will come around, and then we've got a reversed current. It'll accelerate this way, enter a field. So we've got this field, which can be alternated or changed if required, and the particle heading. Now, because it's accelerating, the diameter of its turn increases, and it accelerates quite rapidly until it leaves the cyclotron and hits the target. Very simply explained, but we're using electric fields created by this alternating current between these two, and a magnetic field to turn the particle. With increased acceleration or speed of the particles, the diameter of the turn, if you remember, increases. And the target could be in this oxygen, carbon, nitrogen, something that we want to change. So from oxygen 16.8 we want to become oxygen 15.8. And that's our isotope that we want to use for tagging other materials. These targets will have more protons than neutron and then become unstable. One of those protons that we've added here, so if I use a proton and I add protons to the target, it will become less stable. One of those protons then decays to become a neutron, and that releases a positron and a neutrino. Just need to remember that those elements produced in a cyclotron usually produce positrons, and they are used in PET scanning. Nuclear reactor substances usually produce particles, other types of emitters, gamma, alpha and beta emitters. Gamma emitters are the ones that are most commonly used for scanning, such as technetium 99M.